Hello everyone and welcome back. My name is Mr. Kovault and in this video we're going to be going over heats of reactions. All right, so what do we mean by heat of a reaction? Well, the heat of a reaction is the amount of energy change that's involved in the reaction. So sometimes this is exothermic, sometimes this is endothermic. So there's a lot of different ways to calculate or measure the heat of a reaction. One way is using bond energies. You could use the sum of the bond energies of the products minus the sum of the bond energies of the reactants. You could use other ways of calculating it as well. Here we're going to talk about how you can use heats of reactions in order to use stoichiometry to calculate how much energy is released when you say have a certain amount of reactant that is reacting or a certain amount of product that is produced. Okay, so a couple of things. Delta H, here's an example when we have two aluminum. So we have two aluminums going to react with iron 3 oxide. And when that happens, you form two iron and aluminum oxide. And then in the process of this reaction, energy is a product. And so that energy is 851.5 kilojoules. And so in this case, because energy is being released as a product, then the delta H of the reaction or heat of the reaction. So delta H of reaction is what the symbol or the what we use to indicate heats of reaction. So delta H of reaction here is going to be negative because heat is released. It's an exothermic reaction. So negative refers to the loss of energy. So it is a product. So that's going to be negative 851.5 kilojoules. If we were to reverse the reaction, right, so instead we have two iron reacting with aluminum oxide, we're going to add energy to get this process to go. So we need to add energy in order to convert this into two aluminum plus iron 3 oxide. So in this case, because energy is absorbed during the reaction, the heat of the reaction is positive. So the delta H of the reaction is a positive 851.5 kilojoules. So you can see that the difference in the heats of reaction between this reaction, and its reverse is just a difference in sign. Same magnitude, but the sign is different. This is negative, therefore it's exothermic. Heat is a product. And here, the heat of the reaction is positive, meaning it's being absorbed, and therefore it's endothermic. So as I have written here, if delta H is negative, that means that energy is released and therefore exothermic. Heat is a product. Here, if delta H is positive, then energy is absorbed and it's going to be endothermic. Therefore, heat is a reactant. And so that's what you want to know regarding delta H and the signs. So sometimes you're going to want the heat of the reaction to be per mole. A lot of times when they give you heats of reactions in a table or a chart or something, it's usually kilojoules per mole of reactant. And so if you want to if you want your heat of the reaction to be per mole of a certain substance, then all you need to do is just take the per mole ratios into account. So for example, if we were to use this reaction here with a 851.5 kilojoules of energy released, then we would just take the negative 851.5 kilojoules for the reaction per one reaction, and then say, okay, well, we're going to convert that to moles of aluminum. So we know that for this reaction, it's a balanced equation. We have 2 moles here. So for this reaction involving 851.5 kilojoules of energy released, well, that took 2 moles of aluminum. So if we want a per mole of aluminum, then we use this ratio, this conversion factor that for every one reaction balanced equation, then that requires 2 moles of aluminum. So the reactions cancel out and we get 2 moles of aluminum in the bottom. So that means that this involves a negative 425.75 kilojoules of energy released for every mole of aluminum that reacts. And so here's a sample question that you could be asked. So you could be asked, calculate the energy released when you have 135 grams of aluminum is reacted. So here we're having aluminum is reacted, so we're going to use this equation. We know that the delta H of reaction is negative 851.5 kilojoules per the reaction. We also just calculated that the number of moles, the number of kilojoules per mole of aluminum is this right here. So we can use this now as a conversion factor to calculate the amount of energy released per mole of aluminum. So first thing we want to do is take the given. So they're giving us 135 grams of aluminum. So we're going to take 135 grams of aluminum over 1. And we're going to start to multiply by a conversion factor. So the first thing we want to do is convert to moles, because then we can use our mole ratio. We can use this to convert to energy. So the first thing we want to use is the molar mass of aluminum to convert to moles. And so the molar mass of aluminum is 26.98. So 26.98 grams of aluminum go on the bottom, and 1 mole of aluminum on top. So grams of aluminum cancel out. Now I have moles of aluminum, and so now I can use my mole ratio, right? So I know that in here, if I'm given this, then I know that, okay, one for every reaction, right? So for every reaction, I have I have 2 moles of aluminum, and so now I can take this and I can say, okay, well, for every 1 mole of aluminum, this requires this much kilojoules to be released. So I can put 1 mole on the bottom. So 1 mole of aluminum on the bottom, and I got negative 425.75 kilojoules of energy on top. So moles of aluminum cancel out, and then I calculate that out, and I get a negative 2130.3 kilojoules of energy released from 135 grams of aluminum reacting. I could have also added a second step here. So instead of going straight here, if I'm not given this, then I can just go ahead and use the given delta H of the reaction. So I can then, instead of jumping here, I can first multiply this. So I'll have moles of aluminum, and then I can use the per reaction, and then I can put one mole of the reaction, or one reaction on top versus kilojoules, right? So I could put one reaction gives me number of kilojoules or per mole. Sorry, I'm stumbling over my words. So here I have 1 mole of aluminum. I know here that for every 1 reaction, I get 2 moles of aluminum. So I can have from here, I can put 2 moles of aluminum on the bottom with 1 reaction on top. And then for my last one, I can use, well, for every 1 reaction, I get negative 851.5 moles. So another way just to kind of write it out, so that way it's clear, because I'm stumbling over my words, and and I'm sure it's not clear. So what I could do instead is, well, I know that for every one reaction, I have 2 moles of aluminum. Well, here I have moles of aluminum. I could put 2 moles of aluminum on the bottom for every one reaction. So moles of aluminum cancel out. Now I have one reaction. Well, how much heat is given off per reaction? Well, it's this amount here. So then I can use that as my last step. So for every one reaction, so one reaction goes on the bottom, I release 851.5 kilojoules. So I put negative 800, oops, where is it? 851.5 kilojoules of energy. So reaction cancels out. And if I calculate it again, I once again get the same answer, which is negative 2130.3 kilojoules of energy. So either way works. So I hope this was helpful. This is heats of reaction. You can use heats of reaction in stoichiometry problems, just like I showed here. So if this is helpful, if you learned something from this video, then by all means, like this video, share this video, hit that like button, subscribe to my channel, make sure you hit that notification bell. And when you do, click all so you can be notified by all my videos. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.